Okay, good morning, everyone. Just a reminder, obviously the computer skills test is on this afternoon. Make sure you only go to your allocated practical. Everyone should be turning up, so can't guarantee computer space if you don't turn up to the correct practical. Okay, so this week, again, we're doing something a little bit different. We're talking about correlation, which is something that I think maybe most of you are familiar with. You've come across maybe doing lines of best fit, for instance, in high school or even some of your other subjects at uni. It's a very common procedure in any kind of science. So we'll talk about correlation, and then we'll talk about simple linear regression, which is basically finding lines of best fit. So correlation is about comparing two quantitative variables. So what we've done so far is we've done single quantitative variables. That was when we did single sample t-testing. So we had one sample from one population. It was a quantitative variable. We were testing for, whether or not its mean was equal to or different than a given value. So a single quantitative variable. Then we extended that idea and we went to a quantitative variable grouped by some qualitative variable. So that would be independent samples testing, like male and female scores in biometry or reaction time or whatever. And we looked at independent samples or paired samples, and then we went a little bit further and looked at analysis of variance and blocked analysis of variance. So we still had a single quantitative variable. Well, we had more than one quantitative variable. It was a mean that we were interested in all of those cases, grouped by some qualitative variable, gender, campus, whatever. They were the kinds of examples we had in the pracs. So now we come to sort of the last part, not just a single quantitative, not quantitative by qualitative. What about quantitative by quantitative? How do we compare two quantitative variables to each other? And that's what correlation is about. So we're going to look at a specific set of data. It's a new set now. I'm not talking about like and again or anything like that. Is the height of an individual related to the length of the metacarpus? So the metacarpus is these bones in your hands. Seems like a weird question to ask. Why do we care about the height of a person versus some bone in their hand? It's very important to anthropologists because anthropologists try and study, obviously, skeletons that they've dug up that are varying levels of ancientness, tens of thousands of years old. It's incredibly rare, in fact, almost impossible to get a complete skeleton when you're doing these kinds of archaeological digs. So they have to extrapolate a lot based on skeletal fragments. So if I want to work out, what was the height of this human-like species that existed 100,000 years ago, based solely on the fact that I've got a few hand bones and some thigh bones and stuff like that, this is where it might help us. We might be able to say, given everything else that we know about anatomy and biology and how, a species must logically be structured to, survive, we may be able to work out, obviously with some margin of error, what their height was based on the length of a bone in their hand. Okay, so they have to do little clever tricks like that. Obviously, as I said, with a margin of error. But that might be something you'd be interested in asking. Is the length of this bone in your hand related to your height? If we can find some statistical evidence for a correlation between the two, right? The bigger the bone in your hand, the taller you are. You might expect to see that kind of correlation because you'd expect overall your skeletal structure is proportional, right? If I'm a big person with big hands, I'm probably going to be quite tall as well. Okay, maybe you get exceptions to that rule, but by and large that would be the case. Okay, your skeletal structure is going to be proportional. Bigger the hands, taller you are, etc. So we want to look for a correlation. Is your stature, your height, basically, is your height related to your metacarpus length? So how do we analyze that? Well, we just go out and collect data. We take pairs of observations. Again, we take single individuals and measure two things for every individual, the length of their metacarpus and their height. So we have two quantitative variables. And this is something that I think you've probably seen at some point, at least, in your uni career or in high school or something like that. It's just a scatter plot. And it's a way of representing the relationship between two quantitative variables. So along the horizontal axis, or x-axis as we often call it, we've got the length of the metacarpus, and then along the vertical axis we have their stature, their height. So every point is one individual. Every point is a single individual. So this person here, whoever they were, their metacarpus length was about 41, must be in millimeters, and their height was about, let's say, 163, 64, something like that, centimeters. Okay? So that's for a single individual. Every point represents one person. Okay? So this is what we want to do. We want to look at a plot like this and say, does it seem like there's something going on? Does a bigger metacarpus correspond to a taller person on average, right? So you can see by looking at the plot, I mean, it's not a huge data set, is it? There's only 9 points. It's not a huge data set, but you might suspect that there is something of a relationship there. Okay, it seems like the bigger the metacarpus gets, the taller the corresponding person was. Okay. As always, though, in statistics, we don't just want to get that kind of vague qualitative sense. We need to quantify this. It is possible that we could have gotten these results just by chance, where there is no relationship at all. We take a sample of only 9 people out of the population, measure the length of this bone in their hand and their height. It is possible that you could get something that appears to show a relationship, but you go and do it again with another 9 people, it might show nothing at all, right? So how likely is it that this is due to chance? That's the same thing we've been discussing over and over for the past 5 weeks or something. How likely is it to get data like this purely by chance when there actually is no relationship between the 2 variables? That's what we're going to try and answer. So first off, a little bit of terminology. The variable that we want to predict, the one along the y-axis, the vertical axis, is called the response variable. And just to make your life a little bit annoying, explanatory response, predictor, and no, we'll leave it at that for now. So response is the one along the y-axis. The predictor is the one along the x-axis. They are given those names because that's the relationship that we expect to appear. One of them should predict or cause the other one. The one that we think is going to predict or cause the second variable is the predictor, and that goes along the horizontal axis by convention. The other one that responds to changes in this one is called the response variable, and it goes along the y-axis. So that's just the terminology. One variable responds to changes in another. Okay? So we call that one the response. This one should predict those changes in the other. We call that one the predictor. Okay? Any questions so far? So just the terminology. Every point is an individual. The x location, dial in on the graph. You get your x location. If you're asked to do this in an exam, be as precise as you can. Get out a ruler. Try and get roughly, I didn't get towards the center of that. Let's try again. Roughly somewhere towards the middle. There you go. That'll give me my x value. Looks like it's pretty much bang on 41. And this one, probably somewhere 164 maybe, something like that. Okay? So that's for a single individual. Every point is a single individual. You get the value of the predictor and the value of the response. So other examples might be your hours of study versus your final grade. Both of these things are quantitative variables, right? How many hours you spend per week, that's definitely quantitative. Whether or not we round it off as to being, to the nearest hour or whatever, discrete, continuous, doesn't matter. It's still a quantitative variable, and so is your final grade. If I express it as a number rather than a high distinction, pass, that kind of thing. I expect one to cause the other or affect the other. Which one out of those two, hours of study and final grade, would you say is the predictor variable? Hours of study, exactly. I'd expect the hours of study to explain your final grade, not vice versa. Okay, your final grade, you can't have a cause and effect relationship. You can't go backwards in time, right? You get your final grade, that doesn't then cause your hours of study to change in the past. So in that case, it's very clear because there's a linear relationship. It's actually in time. I do this first, then that happens. Sometimes it's not that obvious. Sometimes they're around the same time. It's not very clear which one is causing the other one, okay? Rainfall versus crop yields, pretty much the same thing. Rainfall is, again, a quantitative variable. I'd measure it in millimeters. That's the standard in meteorological circles. How much rainfall did I get versus how much crops I grew at the end, measured in whatever, tons or something like that. The rainfall should explain or predict the crop yields, okay? If I have a drought, I'm going to have fewer crop yields. If I have a good rain season, I'm going to have better crop yields, okay? That's the rough idea. I mean, some crops don't like that much water, but that's the rough idea. One responds to the other. Crop yields respond to rainfall. The rainfall is not caused by the crop yields. So that's predictor and response variables. So scatter plots are very useful. They're a good graphical representation. We've looked at box plots before, for instance. That's quantitative by qualitative. You've got 2 or 3 or however many qualitative categories. And we say in each one of these categories, what was the value of the quantitative variable? And you get a box plot. When you get a scatter plot, that is quantitative versus quantitative. So correlation, I think intuitively you know what it is, but we're going to be very precise, as always, in statistics. Correlation measures the extent of the linear relationship between 2 quantitative variables. And the key word there is linear. There are lots of types of relationships that you can have between quantitative variables. Okay, there's an infinite number, really. There could be some pattern, some kind of function that explains how one is responding to the other. That is completely nonlinear. But it's not something we're ever going to worry about in this subject. The only thing we are interested in is linear correlations. And what do I mean by linear? I mean something that could be roughly expressed as a line. That's what linear means. That's not a very precise definition. But as I said, I'd be looking for a line that best fits this data. It looks like, on average, roughly, there's a straight line relationship between these two things. Okay? It's not a relationship that looks like this, right? That would be nonlinear. It's not a relationship that looks like this. That would be nonlinear, or like this. It's not any kind of curve relationship. It's a linear relationship. It's a line. That's what I mean by linear. And that's the only thing that we're going to be looking at. There's lots of different types of correlation, but we are only going to concern ourselves with linear correlation. And this is how we're going to measure it. This formula, you can see it once and then forget it forever. It's one of those things that you're never going to be tested on, just like that formula for the degrees of freedom for, what was it, I think the independent samples test. And when you can't assume that the variances are the same, we had that really complicated formula for degrees of freedom. It's called the Welch-Satterthwaite approximation. It's there to show you where you get it from. If you've got a high level of maths, then you can look at that and maybe intuit something from it. Aside from that, don't worry about it. It's not something you're ever going to be tested on, okay? But this is what we're actually going to calculate. What I will do is, instead of using this formula, I'm going to use something that is entirely equivalent. And it's this one, okay? As I said, don't worry about the formula too much, but I do want to at least show you this one, because this one is going to help me explain what a correlation is and how we calculate it, okay? So I'm going to break it down for you, and then I'll prove very quickly for anyone that's interested that it is completely equivalent to the other one that I just showed you. This formula, if I break it down, is z-scores. I've got z-scores for all of my predictor variables and z-scores for all of my response variables. So if you remember what a z-score is, a z-score just tells you how far away is this observation from the mean in terms of multiples of the standard deviation, okay? So I say, here's my number, how far is it from the mean in terms of multiples of the standard deviation, okay? So the correlation is actually the sum of the products of these z-scores, one for x and one for y, for every single point on your scatter plot. You say, what's the z-score in the x direction? What's the z-score in the y direction? Multiply them together. Do that for every single point, and then add them all up, okay? Once you've added them all up, you take the average. Again, it's not exactly the average, is it? We're dividing by n minus 1 instead of n, but that's because that's the number of degrees of freedom we have, okay? So it's kind of like an average product of z-scores. So if I were to go back and look at the picture, actually, yeah, I'll leave it at that because I've got an example coming. I've got a picture coming that'll be, I spent a lot of time working on it, so appreciate it. All right? So don't worry too much about this formula. As I said, you never be expected to apply it or remember it. I will reiterate that the stuff we discussed before the break, the chi-squared test formula, the test statistic for that, that is definitely testable, okay? So I will point out specifically when we come across formulae that you are expected to know and to use. This one is not one of them. But this is entirely equivalent to the other one. And it's a two-line proof. If maths isn't your thing and algebra isn't your thing, then you can close your eyes and go to your happy place. Don't worry about it. For anyone who did advanced maths, you can take a quick look at this just so you're convinced that they are the same formula. So this is the one I'm using in terms of z-scores. If I go to the top line and rearrange that, here in the denominator, this one here is sigma x. That was the standard deviation of x, right? That was what this was over there. Standard deviation of x, we calculate that as the sum of all the squared deviations from the mean divided by n minus 1, and then we square root the whole thing. And this one here, similarly, is the standard deviation of y. So so far all I've done is substitute the actual formulae for the standard deviation into that. All good so far. When I do that, I've got a divided by the square root of n minus 1 times by divided by the square root of n minus 1. Both of those square roots of n minus 1 end up in the numerator. When you multiply them together, you just get n minus 1, which will cancel with that factor of n minus 1 there. Okay? And then that's what you're left with. That's the formula we had on the slide. So it was a two-line proof. Okay? It's entirely equivalent to the one that was on the slide. So as I said, that's not necessarily important for you to know, but I just did want to prove that this one is the same as that one because I'm about to use this one instead because I think it's better. I think it makes more sense. I think it's easier to read. There's a whole number of reasons why I prefer this one, so I'm going to use that one. So in the end, all this is, like everything else we do in statistics, this is a way to quantify something. It gives us a single number. You'll plug all your numbers into this. Realistically, you won't. Our commander will do it for you. And you'll spit out a single number. And that number will tell you how correlated your x and y variables are. That's all it is. A single number to quantify that idea of correlation. How closely tied are they, right? I want to work out someone's height based on the length of a bone in their hand. How closely linked are those two variables? Is it really, really tight, or is there basically no relationship at all? That number will tell me. That's all it is. The correlation coefficient. A couple of properties of the correlation coefficient. It has to always be between -1 and 1. Okay? Always between -1 and 1. If you ever get a correlation coefficient outside of that range, well, you've made a mistake. That's not possible. If someone tells you they have a correlation outside of that range, not possible. They must have made a mistake. If you get a correlation of exactly 1, +1, then the scatter plot that corresponds to that would show a perfect straight line relationship between the two variables where it's increasing. It goes from the bottom left to the top right. We'll show you a picture in a second. If the correlation coefficient comes out to be -1, then it's still a perfect linear relationship, but it's sloping down. The scatter plot will have points exactly lying on a line. You could draw a line through every single one of them, but they would be sloping down. It would be a decreasing line. So +1 and -1 are as strong as each other when it comes to deciding the strength of the correlation. How good is the correlation? They're as strong as each other, but they will just say, is one sloping up or is one sloping down, plus or minus. The notation that we use for the sample correlation coefficient is R, and sticking to the convention we've used in the past, mostly, the population correlation coefficient looks like a little p, but this is the Greek letter rho, spelled R-H-O. So there's another Greek letter to add to your lexicon. Okay? Again, that's just notation. Don't let it throw you. So there is a true population correlation coefficient, which we will almost never know. The point about statistics is we're going to take a sample and then calculate the correlation coefficient from that sample data. And we call that R, the sample statistic. Happy so far? Yep. So here's some examples of correlation. In the top left, you've got a scatter plot that would have a correlation coefficient equal to +1. Every single point in the scatter plot would lie on a line, if you could draw a line through all of them. Okay? This is a perfect linear relationship. It's as strong as it possibly could be. You can't get a stronger linear relationship than that. Okay? Conversely, if you look at the bottom right, this is also a perfectly strong linear relationship. Can't get stronger than that, except the only difference is the correlation is -1. It's sloping down. Okay? But it's still a linear relationship and still a perfectly strong one. And then you've got everything in between. The one that's in the center, this guy here, is a bit all over the place. And that's sort of represented by the correlation coefficient. If you were to calculate it for every single point on that plot and add up all those numbers, you'd get a correlation of 0. Okay, there is no relationship between those two variables. And then the other in-between ones, this guy here, correlation of negative 0.4. So it's a negative correlation. There's still some kind of correlation going on there, but it's not a very strong one. Okay, it's 0.4. The biggest it could be is 1 or negative 1. So you can see there is a trend in the scatter plot. It looks like it's decreasing. As you increase in the predictor variable, the response variable goes down. It does look like there's a bit of a relationship, but it's a bit loose, isn't it? It's not a very strong relationship. Conversely, I could have something exactly as loose or tightly correlated, however you want to think of it, down here. This one is as well correlated as the other one, except it's a positive relationship. Its correlation coefficient is 0.4, positive 0.4 instead of negative 0.4. They are as strong as each other, but this one is sloping up and the other one was sloping down. So that's the thing to take away from it. Correlation coefficient can only be between plus or minus 1. Those two extremes represent perfect correlations. Everything in the middle is obviously something in the middle, okay? But whether or not it's positive or negative doesn't tell you about the strength, it just tells you about the slope, whether it's increasing or decreasing.
Wouldn't 0 be perfectly horizontal?
Yes, if you had a horizontal one as well, it would be 0. Yep. So 0 will come up, it actually comes up, it's like, if it's horizontal, it will be 0, but just because it's 0 doesn't imply it's horizontal. Yep, it'll come up more than that. I'll show you a couple more, just to get the idea. Here's a few scatter plots. Okay, we haven't bothered to draw the x and y axes because we don't need to. We just want to get the idea across. In the top row, you can see a bunch of kind of blobby scatter plots. Okay, and it's showing you the correlation coefficient for each one. Over there, you have positive 1 because it slopes up and every single point in the scatter plot is on a line. And then as it gets weaker, as the correlation between the variables gets weaker, it starts to look more blobbish, if you like. The coefficient gets closer and closer to 0. And then over here, it swaps over to a negative correlation. And still, 0.4 is as strong as negative 0.4 in terms of how correlated the variables are. But you'll just notice that now this scatter plot has a blob that's sort of angled the other way until you get to negative 1 at the other extreme. The middle row is there to really sort of stress the fact that the correlation coefficient itself it's not the slope. That's a key mistake that a lot of students make. They think that the correlation coefficient is the slope of that scatter plot or the line that you could draw through it. Every single one of these scatter plots has a correlation coefficient of 1. Okay? It's got nothing to do with the slope. They're all perfectly correlated, and same for all the negative ones. The only thing that the correlation coefficient shares in common with the slope is its sign. Positive correlation means it must be a positive slope. Negative correlation means it must be a negative slope. But that's where it ends. The actual number, 0.4, 0.8, whatever it is, has nothing to do with the slope. Okay? And the last one is a bunch of very obvious patterns in scatter plots. Super obvious there. If I got a scatter plot that came out like that from my data, I'd be pretty certain something's going on, right? There's some relationship between the variables. But you'll notice that the correlation coefficient for all of them is 0 because they're not linear relationships. There is a relationship, but it's not a linear one, okay? So you'd have to use some kind of other analysis to look at what's going on, okay? And there are other analyses, but they're not something we would do in this subject. Everything we do in this subject will be linear relationships. It'll be stuff like in the top 2 rows. Okay? Happy with that so far? So the correlation coefficient is just a number. It tells us how strong the correlation is between a couple of variables. So I just want to give you an intuitive idea as to what the number actually is. I mean, it's between -1 and +1. Where does that number actually come from? So we'll start with a scatter plot. I've made it have a negative relationship, so it's not a perfect linear relationship. You can see these red points on the scatter plot, they're a little bit spread, but it does look pretty linear, but also obviously pretty negative as well. As I increase in the x direction, the y values decrease, so it's going down. I've marked on the x and y axes the mean for each of those sets of numbers, the x mean and the y mean. So if I looked at every single point, here's one point here, I'd look at its x variable value down the bottom, somewhere down there. the next one, somewhere down there, and so on and so on. Add up all of those values, divide by the number that I have, and I would get a single number. I would get the mean of the x's, okay? And then I do the exact same thing for all the y's. What were all the y values for each point on the plot? Add them all up, divide by the number I've got, I'll get the y mean, okay? Easy as that. We've done means before. So what does the correlation do once you've got this information? Once you've got a scatter plot and you've got the means of both of your data, what does the correlation do? The correlation coefficient is really like an average area. This was the formula that we had. What I'm going to do is I'm going to do a transformation on the scatter plot. I'm going to take all of those points in the scatter plot and turn them into their z-scores, okay? So I've got an x variable somewhere here. If I look at, say, this guy here, mark it down. I want to know how far away is that variable from the mean in terms of multiples of the standard deviation. So I'd take the number, here's my little guy, I take the number, subtract the mean, divide by the standard deviation. It would give me a z-score for that particular value. I'm going to do that for every single point, work out the z-score for the x's and the z-score for the y. So I'm doing this transformation. Okay, every x value will now go to its corresponding z-score. Every y value will go to its corresponding z-score. Where will the means end up? X bar and y bar. What will they get sent to? If I redraw this scatter plot now in terms of z-scores instead of the original data, where will x bar and y bar end up? They're going to be shifted. Shifted to what specifically? You don't need to know the numbers. You just need to know what a z transformation is. If I ask the question, how far is this from the mean in terms of multiples of the standard deviation, I'll get some number. If I ask the question, how far is this from the mean, how far is it from the mean? 0. It is the mean. The z-score is 0 for that. And the z-score is 0 for the mean of y. So both of those numbers get sent to 0, 0. And if I do that to the whole plot, I get a new scatter plot. I've basically just taken all those points and shifted them a little bit. The x and y axes are now the zx and zy axes. They represent z-scores, okay? So I've just moved everything a little bit, and there was some stretching that goes along the axes, but don't worry about it. So I've got a new scatter plot, and it's the same information as what I had originally, but now I've represented all the number just in terms of how far they are from the mean in terms of standard deviations. Am I 1 standard deviation above the mean, 2 below it, whatever, okay? And here's the neat thing. If I dial in on a single point, I'm going to look at this single red point at the top left. The numbers along the x and y axis represent the z-scores for that point. How far was that point from the mean of the x's in terms of standard deviations of the x, and same for the y. If I multiply those two numbers together, I get like an area, okay? Everyone knows how to calculate the area of a square or a rectangle. Multiply length by breadth. So I've shaded this black area. Problem is the area is going to be negative, okay? Because I'm looking at a scatter plot, I'm in the negative area for the x's, but the positive for the y's. So this is going to be negative times positive. I'll get a negative area. Okay, I put it in quotation marks because obviously area isn't normally negative. But that's what it will come out to be, purely when I multiply the numbers by each other. X value times y value, and I get an area. So that's for one point. And then I just repeat that process over and over and over again for all the points in the plot and add them all up. Some areas will be negative, some will be positive. Okay? Any area that comes out in the top right will come out to be positive because it'll be a positive number times a positive number. Anything down here will also be positive because it'll be a negative times a negative, come out to be positive. Anything in the top left or bottom right will come out to be negative, which is why the correlation coefficient will come out to be negative if you're sloping down and positive if you're sloping up, because the scatter plot will have most of the points in those areas, positive and negative areas. So we add up all of those areas, and then we take the average. That's what this formula is telling you. The product of z-scores. You get an area in your scatter plot when you multiply the z-scores by each other. When you add them all up and divide by n minus 1, it's like getting the average area. That's what the correlation is, okay? The more tightly correlated your variables are, the closer that will be to either -1 or +1. The looser they are, the closer that will be to 0, okay? If you get a lot of points spread over all 4 quadrants, you'll get a lot of negatives and a lot of positives, and they'll all cancel each other out, and you'll get something pretty close to 0. But if you have something that is tightly correlated, which this one here is reasonably tight, you'll notice that there's a couple of points that are in the positive area, but most of the time, it's going to be negatives added to negatives. I'm going to get a negative number at the end, okay? So that's what the correlation coefficient is, in a sense. Well, not in a sense, it is. It's the average area in a scatter plot. That's what it tells you, okay? And at the end, you'll get a number for your average area. It must be between -1 and 1. I'm not going to worry about why. This is probably pushing it, showing you this. But it will be between -1 and 1. Whether or not it's negative or positive will tell you the direction of the correlation, sloping down or sloping up, okay? Any questions about that? All good? I will put this one up on views as well in those pictures. Really, the only takeaway I want you to have from it is to just understand roughly what the correlation is. It's a single number, gives you an idea of how tightly correlated they are and in what direction, negative or positive. So let's take a look at I shouldn't have shown you that because I just want to go back and show you the scatter plot, right? So we're going to actually apply this now. This was our data, 9 points of data, length of metacarpus, and stature, a person's height. Looking at that, is the correlation coefficient going to come out to be positive or negative? That's the first question I want to ask you. Positive, right? It's sloping up. As metacarpal length increases, height also increases. There's a positive relationship between the two variables. Ballpark the number for me. What do you think the correlation coefficient might be? Given that +1 would be a perfect correlation, and this isn't perfect, roughly where do you think the number will be? Has to be positive, so that's your start. 0.7, 0.8. Yeah, it's a reasonable kind of thing, but it still looks a little bit scattered, okay? So you ballpark the number. I'm not expecting 0.1. That would be a terrible correlation. That's almost 0, right? I'm expecting, something pretty reasonable. Or as always, think about the numbers before you do any kind of calculation. You'll know if you've made a mistake. In actual fact, it comes out to be a bit bigger than we expected, 0.856. Reasonably strong correlation, okay? So how did we calculate that? They've got on the left-hand side all of the raw data. So there's 9 individuals, 2 observations for each, metacarpal and stature. To use the formula that they used, you need to work out the sum of all those products, xi minus x bar, y minus y bar. They've done that for you. That's not something you'd ever be expected to do yourself. And then you work out the sum of all the squared deviations. Both of those appeared in the formula as well, okay? Once you've got all those numbers, you can plug them in to that formula, if you're so inclined, and you'll get 0.856 is your number, okay? What I would recommend, as I said, you're never going to be expected to use the formula yourself, but I would recommend you do a really simple example just once in your life to give you an idea. Pick 3 numbers, okay? Something that's clearly on a line, a perfect line. So you might pick 2, 2, 1, 1, and 0, 0. Pick those 3 numbers and work out the correlation coefficient. Do it yourself by hand. It won't take that long. But there's a whole number of reasons why that's a good idea. One, you have to work out the standard deviation or the squared deviations. You have to work with the sum symbol, all that kind of stuff. It's good practice, okay? It's good practice to understand those concepts. And also, again, to get your head around the summation symbol, which you will have to use for the chi-squared test functions, right? So plug it all in, work it out. You should get a correlation coefficient of +1. You know what it was going to come out to be. They're all exactly on a line, y equals x, okay? And then just change one of the numbers. Any number, doesn't matter, and change it however as much as you want to. Maybe I'll make this 2, 3 instead. And then recalculate the correlation. You'll find you'll get something less than 1 now. It might be like 0.8, okay? It's always a good idea just to play around with the numbers a little bit, to get your head around the concept, to try and understand it a little bit better. Hey, I changed this to the numbers, what happened to the correlation coefficient? That kind of thing, okay? You don't need too many numbers, you need 3 at least, all right? It's always linear if you've only got 2 numbers, right? You just draw a line between any 2 numbers. It's always linear if you've only got 2. So you need at least 3 numbers. Pick any 3, work out the correlation coefficient yourself and see how you go. So there we go. It looks like there's a pretty reasonable correlation between our 2 variables. Metacarpal length is pretty strongly correlated or related to your height, your stature, okay? But that was from a set of sample data and only 9 observations at that. So the question we've been asking throughout the entire unit, pretty much, the main crux of the argument was, this is what we got from our sample data. Is this a significant result? What is the chance that I would have gotten a correlation coefficient this big, even if there were no relationship? It is possible to take 2 variables with no relationship and draw out a random sample from both of them. And it is possible to see a relationship sometimes even when one doesn't exist, just by virtue of random sampling. Okay, it is possible, but is it probable? So we need some way to get a p-value from a test statistic to answer that question. We've got our sample statistic, R. We want to say, how far away is this from what we expected in terms of some kind of standard error? So we do a hypothesis test, like we've been doing for weeks and weeks now. But again, it's a little bit different. Most of what we've done in the past was to do with means, or a difference of means, mean difference, whatever. Now we've got a new parameter. The parameter is the correlation coefficient. The null hypothesis states that there is no relationship between the 2 variables. If that is true, the correlation coefficient should be 0. No linear relationship, okay? We say nothing about anything else. Not worried about others. So the correlation should be 0 if there's no relationship. We simply want to test for whether or not it is significantly different from 0. Okay, is it different enough from 0 to indicate there really is a relationship between those 2 things based on our sample data? So you can do one-sided tests for this. You can test specifically for a positive correlation or a negative. For now, we're not going to concern ourselves with the direction. We're just going to say, is it significantly different from 0? Because as I said, 0.8 is as strong a correlation as negative 0.8. Okay, so the sign of it, positive or negative, doesn't matter too much. I just want to know, is there a relationship? So there it is. There's our null and our alternative hypothesis. What is our test statistic? We're not going to do a big song and dance about the test statistic because you've seen it so many times now, and it's not that critical. As long as you understand that a test statistic quantifies how different your sample data is from what you expected it to be. It looks different from any other test statistics we've done, doesn't it? In fact, it's the exact same idea. I'll just show you very quickly. This is the idea we've had in the past for all of our other test statistics, basically. Well, except for analysis of variance, I guess, and chi-squared test. We get our sample statistic. We want to say how big is the difference from the null parameter, and then we divide by something called the standard error, okay? The spread of all of the possible sample statistics we could get according to the central limit theorem. That's the standard error. So we won't go into a discussion as to what the standard error is, but for instance, we know what our sample statistic is. That's R. The value of the null parameter will be what in the calculation? What are we testing for a difference against? Different from what? 0, okay? R minus 0, that'll be the numerator. The standard error is this thing. It's the square root of 1 minus r squared over n minus 2, okay? 1 minus r squared, there's a reason why that number is there. We're not going to talk about it in this subject. N minus 2, at least I can say that's the degrees of freedom for that number, 1 minus r squared. So that's the square root, that's your measure of the standard error for this particular test statistic. For this particular sample statistic R, okay? And if you're dividing by a fraction, as you know, you can change that to a multiplication by the reciprocal, and you end up with what we have here, okay? So I just wanted to show you that the same idea is still applying. We're still saying how far away are we from our null parameter in terms of a standard error. The standard error changed. That was pretty much the only thing that did change, okay? So that's our test statistic. There it is. So to get a p-value, having a test statistic is all well and good, but we need to know what kind of distribution it follows. Where is the probability going to come from? Is it going to come from an F distribution, a chi-squared distribution, a normal distribution? In this case, it's going to come from a T distribution, specifically one with n minus 2 degrees of freedom. So however many points you had in your scatter plot, subtract 2, that's the T distribution you want, that one with that many degrees of freedom, okay? And you'll say, what's the probability of getting something bigger or smaller or twice bigger or smaller, whatever? than this particular number. And that gives you your p-value. So that, again, is the same as what we did for the last 4 or 5 weeks. Any questions so far? All good? So what did we get? We got a sample statistic of 0.856. If you plug that into the formula for the test statistic, R is 0.856 multiplied by the square root of 1 minus R squared, 856 squared, over 9 minus 2. We had 9 points, minus 2, that'll give us the degrees of freedom. That number comes out to be, did I do that right? Yeah. Whoops, other way around. My mistake. Should be 9 minus 2 in the numerator, and 1 minus R squared in the denominator. So you can plug all that into your calculator if you want, but R Commander will work it out for you. And it tells you that the number is 4.380, and the p-value is that. I think maybe it's worth me just showing you how to do that, because the computer skills test is coming up next. And I've got a suspicion that a lot of people are a bit hazy on stuff we did earlier in the semester with regards to getting p-values and that sort of thing. So it's probably worth showing you. So can anyone tell me, I've opened R Commander, I've got a test statistic, 4.38. Where do I go in R Commander to get the p-value? Does anyone remember? Not means. You could use means, you're quite right, if we had the sample data loaded. If I don't have any sample data loaded, I can go to the means submenu, but nothing's going to be there because there's no data to work on. It could do it if the sample data was there, but we don't have the sample data. So if I've only given you the test statistic, where do you go? Distributions. You go to the distributions menu. I want continuous distributions because I want a t-distribution. It's a test statistic from a t-distribution. And I want a probability. So I go to t-probabilities. It asks me, what's your variable? Well, the test statistic I just found was 4.38. So I plug in 4.38. What are the degrees of freedom? 9 minus 2. Do I want lower or upper tail? Now think carefully. Here's my null and my alternate hypothesis. How am I going to calculate the p-value? I've got a positive test statistic. What do I want R Commander to give me, the lower or the upper tail? Sorry? Lower? Why lower? It's not even, you've got to be careful, right? This is something that you've got to do both, really, yeah. Because it's a two-sided test. I want to say, what's the probability of getting larger than 4.38 or smaller than negative 4.38? So I don't actually have to do both. If I just pick the smaller side, it's a positive test statistic, so I'll look at upper tail, what's above it, get that number, 0.016. I need to double that because it's a two-sided test. 2 times that value gives me, gives me 0.0032 roughly, which is what the lecture slide says that it is. That's your p-value, okay? So be super careful. You can do it the other way. You can also, obviously, because the t-distribution is symmetric, if I go back and ask for the probability of getting less than negative 4.38, so lower tail, negative 4.38, comes out to be 0.016 as well, okay? That's why I doubled it. That's the two-sided p-value. So a lot of the, I feel that a lot of the questions that I still get asked are in relation to that. Because it is tricky. Your p-value depends on your test statistic. Here's my t-distribution with n minus 2 degrees of freedom. Okay, here's my test statistic. Well, I'll be specific now. It's got 7 degrees of freedom. 4.38, pretty big test statistic, but I've got a two-sided test. My null hypothesis is that there is no correlation. The alternative is simply that there is, that it's significantly different from 0. So once I get my test statistic, I need to look at both ends. What's the probability of getting something more extreme than either one of these guys? And both of those came out to be about 0.016. You add them together, you get 0.0032. Okay? So it always depends on the alternative. Okay. Worksheet 5 was where we did a lot of those questions, and those are the ones that throw most people. They give you a number, just one number, and an alternative hypothesis. They say, what's the p-value? And everyone usually just writes down the number, okay? It may be the number, it may be 1 minus the number, it may be twice the number, it may be twice 1 minus the number. How you know which one it is depends on what that is, okay? You look at your test statistic, is it positive or negative? What's the alternative hypothesis? Is it greater than or less than? Okay, you have to take those things into consideration to work out the p-value. Okay, any questions? Cool. So there we go. So what did we just do? We just did a hypothesis test. We were looking for evidence that the correlation was significantly different from 0. And we've got evidence of that. That's a very small p-value, right? Definitely smaller than 5%, our most commonly used significance level. Smaller than 1% even. So we have evidence to suggest that your height, your stature, and the length of your metacarpal bone are correlated, okay? There is something going on. There is some relationship between them, possibly, okay? That's what the statistics is telling us. So after all this talk about the correlation coefficient, again, it still boils down to the same basic idea. Null and alternate hypothesis, test statistic, p-value. It was the same for single samples, independent samples, analysis of variance, chi-squared. It's always the same. Null, alternate, test statistic, p-value. Okay? It just so happens now the test statistic changed and the sample statistic changed. Any questions? Cool. So there's a couple of things, as always, that we need to be a bit more precise about. The correlation coefficient assumes that the observations are independent for each variable. Obviously, if you measured the same person twice, you would have 2 points exactly on top of each other, or 3 times or 4 times. Those observations would not be independent, and they would skew the correlation coefficient. The variables themselves can be non-independent. That's the point. Your x and your y variables, there's probably going to be some dependence between them. That's what we're looking for to start with. But the individual observations themselves must be independent of each other. If the variables are completely independent, then your correlation will be 0. There's no relationship between them, okay? However, the converse is not true. Just because the correlation is 0 doesn't mean that the variables are independent. You saw plenty of examples of that. Right? All of these guys, the correlation coefficient is 0, but I would not say that those variables are independent if I got scatter plots that looked like that. Okay? Being independent implies the correlation is 0, but the correlation being 0 doesn't necessarily imply that the variables are independent. And lastly, again, I've said it a few times because it is very important, the correlation coefficient, we are using measures only linear relationships. Any other kind of relationship we are not interested in. Okay, there's another one, by the way, a parabolic relationship. It would also have a correlation of 0. Would work out to be that way. Okay. Next thing, and this is an important thing, from our statistics, I should have been a little bit more careful in the way I worded it. We got evidence that the correlation coefficient was different from 0. That's not actually the same as saying that there is a cause and effect relationship between them. Okay. I've got evidence to suggest that the population, if I looked at all metacarpal bones and all statures of all people, that the population would have a scatter plot that appeared correlated as well, okay? That doesn't necessarily imply that one thing is affecting the other, okay? So just because 2 things are correlated does not necessarily mean that one causes the other. And there's a great website with lots of examples of this. Here's an example of 2 quantitative variables. US spending on space science and technology, and suicides by hanging, strangulation, and suffocation, okay? 2 quantitative variables in a scatter plot. They look very strongly correlated, 0.992 correlation, right? Okay. Would you conclude then, based on this, you would do a hypothesis test if you had the data. You've got your points, you've got your correlation coefficient, you work out the test statistic and the p-value, and the p-value would say, yeah, your correlation coefficient is definitely significantly different from 0. It'd be a very small p-value, okay? Can you then conclude that the more the US government spends on space, the more people are going to die by hanging, strangulation, and suffocation? Is one thing causing the other? No, okay? Unless there could potentially be some bizarre relationship, some reason why these 2 are linked, okay? Maybe engineers are more prone to being depressed than anyone else. I don't know. The more they spend on engineering and science stuff, the more engineers and scientists there are who lose the will to live. But aside from that, there should be no direct relationship between those two things. They're not causing each other. Here's another one of my favorite examples. So this side is, I'm not sure how to pronounce his surname. His name is Tyler Vigen, I think. You can check out this site yourself. It's very clean and easy to look at. Number of people who drowned by falling into a pool correlates with films Nicolas Cage appeared in. Okay? If you ever needed another reason to ask Nicolas Cage to stop, there it is. Obviously, it's not a linear relationship, is it? Okay, but this is more general. This is talking about just any kind of correlation. They correlate, okay? You could, again, if you were looking at non-linear correlations, you could do some kind of statistical test and say, yes, the p-value is very small. This is very obviously a correlation different from no correlation at all. Doesn't mean one is causing the other, okay? Nicolas Cage is not causing people to drown by falling into a pool. The point is, if you look at enough data across enough different variables, eventually you're going to find correlations. In fact, you have to find correlations, okay? It'd be amazing, really, if you didn't. Just because they're correlated doesn't necessarily mean that one causes the other, okay? So you have to be careful. The statistics will get you so far. It'll tell you if there may be a cause and effect relationship. It'll definitely tell you if there's a correlation, that it can do, but it just means maybe there's causation. So correlation does not imply causation. That's a mantra in statistics and something that is still heavily misused in everything. I mean, a day can't go by when you read a newspaper article about how sitting at your desk for 3 hours a day correlates with an increased risk of cancer or something like that. Okay? Yeah, it correlates. They gathered enough data, potentially, if they did the study right over decades, which is, you know, again, a bit dicey. Yeah, it correlates, but it doesn't necessarily mean one implies the other. Okay? If you ever want to prove cause and effect, you need to do an independent randomized study. You need to control your variables, and that's something for a different statistics unit that you would do. For us, all we're going to worry about is just the correlation coefficient, okay, with that caveat. Any questions? All right, so it's a good point to take a break. Let's say if you want to come back on the hour, 10 o'clock if you want to take a break, and we'll keep going. Second half will be a bit quicker now that we've gotten all that out of the way. Tyler, T-Y-L-E-R, Tyler Vigen, or Vigen, V-I-G-E-N.
I think there's a similar correlation between consumption of margarine over butter and...
Okay, so we talked about correlation, and it was linear correlation. So the next logical question is, you know, if it's a linear correlation, can we get some other way to not just say that they are correlated, but, you know, get a line, get the equation of a line that we think might describe the relationship as best as we can, given the data that we've been given. And this is called simple linear regression. Simple because there's only one predictor variable. You can do linear regressions with more than one. Only thing we're going to worry about in this subject is one explanatory or predictor variable, and linear, obviously, because we're talking about linear relationships. So we looked at the stature and metacarpal data, and now that we know that they are correlated, we're going to ask, can we predict the height of an individual from the length of their metacarpus? Okay. So again, anthropologists, this is their goal. They want to get incomplete skeletal fragments and say, given this piece or this piece, we can estimate the overall shape and size of the individual based on those fragments. So how would we do that? Again, we collected all that data. We got 9 data points. And we want to say, is there a linear relationship? Yes, there is. According to what we did in the first part of the lecture, there was a linear correlation, pretty strong one as well at 0.85. Can we use that then to predict, with a reasonable degree of accuracy, someone's stature based on the length of their metacarpus? So we're interested in using the x variable to predict a value of the response variable. The response variable responds to changes in the predictor. So the other names that I was going to mention before and I didn't, but they've mentioned it here in the slide anyway, are independent and dependent. Those are the two other names you may have heard for x and y, as opposed to predictor, and response. Okay, they're interchangeable. Statisticians are a bit loose when it comes to some of their notation and terminology. Doesn't matter. I mean, some might argue there's subtle differences in why you would give it one name rather than the other, but really you can just swap them around as you like. So it's either independent or predictor for X and response or dependent for Y. Okay, and then again, they give you the same kind of idea. Your X variable is independent. It's not depending on Y. Y depends on it. Okay, crop yield depends on rainfall. Rainfall doesn't depend on crop yield. Okay, sometimes a relationship is very simple like that. Sometimes it's a little bit more complicated. Sometimes you might be in a scenario where they're affecting each other, which is very complicated. But for our purposes, we're just interested in learning about simple linear regression. So it's going to be nice and simple. We're going to say that the metacarpal length is independent. Your stature is then dependent on that. So what is linear regression? SLR, which stands for simple linear regression. That's what we had at the first slide. SLR is a common abbreviation. It's the equation of a line. We want to find the equation of a line of the form y equals a plus bx plus, and this guy here is another Greek letter, epsilon. Looks like an E. Epsilon, so you can add that to your list. We're not really going to come across epsilon again, aside from introducing it here. Epsilon is noise, is just some normal variation. You get your equation of the line. Obviously, your data isn't always going to fit exactly on the line, right? If it's not a perfect correlation, there's going to be some plus or minus either side of the line. That's all epsilon stands for there, okay? The statistical noise that you would get from normal variation. So you may have come across the equation of a line in high school. In high school, they would have used slightly different notation. They would have said y equals mx plus b. Okay, that's probably the one that you're more familiar with. Can anyone tell me what is m? There's a name for m. What is gradient? Yeah, the gradient or the slope. Whoops, gradient or slope. Okay, it tells you how steep the line is. Does it go up or down? That's the first part, positive or negative. And then the steepness, okay? Is it a shallow line like that? Is it a really steep one like that? It tells you that. Does anyone remember what b represents? The y-intercept, good. So it's the point on the y-axis that the line crosses. Now, if that's what you came across in high school, this is going to be awkward because now we're going to call m is going to be called b, and b is going to be called a, okay? So the m here is now going to be called b, and the b is going to be called a, all right? Obviously, makes a lot of sense. So if you didn't do it in high school, you're actually at an advantage because you don't have all that different notation floating around in your head. What I want to point out, though, is that it should be obvious by looking at the line. The slope is always the coefficient of x. Coefficient is a very fancy, expensive-sounding word for a number that sits in front of a letter. That's all the coefficient is. So whatever x is, the number that sits in front of it is always going to be the slope or the gradient, and this guy here is the y-intercept, the point that it crosses the x-axis. We'll talk a little bit more in detail about them. The point is that all lines have that form. All lines. Doesn't matter what the line is, it depends on only two numbers, the slope and the intercept. Change any one of those two, you get a new line. But that's all there is. So we want to find the a and the b. That's our problem now for simple linear regression. What are those values? Can we find a way to calculate them based on our sample data? Okay? Specifically, we don't just want any old line, we want a line that best fits our data. Okay? So how do we quantify that idea mathematically? Intuitively, I think we know, we can picture in our heads what a line of best fit might look like, but how do we actually get it mathematically? So the conversion between Fahrenheit and Celsius is a linear relationship, okay? If you want to get the degrees in Fahrenheit given the degrees in Celsius, you have to multiply the Celsius value by 1.8 and then add 32 to it, okay? So it's a very simple linear relationship. We're going to see if we can do the same thing for height and metacarpal length. So we're going to have y is our stature, our height, and x is our metacarpal length. What is a and b? That's our question now. So here's some attempts at a line of best fit. These are all the same 9 points that we have in our data. And out of these 4 pictures, which one would you think is a line that best fits or best matches the overall trend of the data out of those 4? Which one do you think is the best representation of the overall trend of the numbers? The bottom right one, okay? The bottom right one, intuitively, I think we all know that. This one up here doesn't look very good at all. That's a straight, flat line. That would indicate no relationship at all, actually. It means that no matter what your metacarpal length is, the stature didn't change at all. It didn't respond to changes in the metacarpal length. That's exactly what we want when we're talking about a linear relationship. We're looking for it to respond to changes in the predictor variable. So that indicates no change. This one here is terrible because the line is far above all of the points. You can see that. These little red arrows are indicating your distance from the line of each point. The next one, again, looks better. It runs through basically the center of the data, but you can see in this one, the red lines are bigger on average than they are in this one. Okay, look at how small all these differences are. Okay, compared to these differences here. You can see you've got 4 big ones, as opposed to here, there's only 1 or 2 big deviations from the line. So I'd probably expect the bottom right to be the best fit for the data. And that's the idea. That's how we quantify the line of best fit. We say which line minimizes the total squared deviations. All of these values. Square each of these numbers that represent the distances, add them up. I want to find whichever line minimizes that total sum. That will give me the line of best fit. Okay? That's how you get the line of best fit. You don't have to actually do it. That would be a calculus problem. Okay? Calculus is well beyond anything we do in this subject, so we don't have to worry about it. But as long as you understand that's where it comes from. Okay? Minimizing or maximizing things is a classic problem in calculus. Not something we're going to worry about, but that is how you would do it. Okay? You want to minimize the difference between the y value on your line, the y value on your line and the actual y value of your point. Okay? This is what the equation of the line tells me I should get, a plus bx. This is what I actually have from my scatter plot for my individual points. What is the squared distance between those two? I want to minimize that total sum. Okay? So the name might be important, residual sum of squares. The mathematics isn't. How we actually minimize that sum, as I said, you need to take a derivative, a couple of derivatives and work it out. It's calculus. Don't worry about it. But that's how we do it. Okay? What's the distance between my point on my scatter plot and my line? So it's kind of weird to think about because you don't know what the line is to start with. How do you work out the distance between the point and the line when you don't know where the line is yet? That's why you have to use calculus. You don't set any of these variables in stone. You give them a name, A and B, work out their derivatives, and you should be able to get the line of best fit based on that. So what it actually boils down to is that your 2 values, A and B, will be given by these fairly complicated looking expressions. The notation, again, has changed a little bit for the sample values. These are the estimated values of A and B. There will be some actual values for the whole population. If we could look at the whole population for the line that best fits all of the population, we don't have that information. We're going to estimate those values from samples. So A hat and B hat are the sample statistics. A and B are the population parameters. It's annoying that they didn't use alpha and beta to stick to our convention of using Greek letters, but there you go. A and B are the parameters. A hat and B hat are the sample estimated values. Okay? Very similar to proportions, right? Remember when we had proportions? P for the population, P hat for the sample. Okay? A for the population, A hat for the sample, and so on. So this is telling you that you can calculate the slope of your line of best fit based on these, SXY and SXX, and you can calculate the intercept based on the means of the x's and the y's and your slope value. So you have to calculate the slope first, then you can get the y-intercept after that. Again, don't worry about the formulas for the sums of squares. You'd never be expected to work them out by hand. This is something that R command will, as always, spit out the information for you. okay? You may be expected just to remember this here. Someone may give you the sums of squares, okay? SXY is a shorthand notation for an idea called covariance. It's very similar to the deviations, the squared deviations for a single variable, but instead of squaring for one variable, we multiply the deviations for one variable by the other. And that's sort of the cross relationship between the two of them, S, X, and Y. The sums of squares S, X, and X is the variation of X with itself and Y with itself, the squared deviations of each of those numbers from their means, okay? So those formulas you don't necessarily need to worry about, but you may need to know, given if someone just tells you this number equals that, this number equals that, you then have to plug them in the correct order to get those values, okay? Why is that? I would like to give you at least, there's a lot going on there mathematically, and none of it would make any sense to you, I'd probably guess, for most of you, which is fine. But I would like to give you some intuition as to where at least this value is coming from. This value is pretty straightforward, I would think, because it really comes from the equation of the line. Y equals A plus BX. That was the equation we were starting with. Y equals A plus BX. If I rearrange that to make A the subject, well, I just subtract BX from both sides. And I get Y minus BX equals A. Okay? My best estimate for A would be to use my best estimates for everything else. Okay? My best estimate for Y would be its mean. My best estimate for X would be its mean. And my best estimate for B would be that value I just worked out from this one here. Okay, so that's where A is coming from. It's a simple rearrangement of the equation of the line, given that you know B based on that formula. Does anyone know how to calculate a slope just for a line? Like if you did it in high school, there was a very simple formula in English. What did you say? You may know it. Anyone else know it? The formula, rise over run, right? Rise over run. So what I want to do is give you some intuition of why this is really rise over run, but for a scatter plot rather than just one straightforward line. So I'm going to take this idea. I'm going to say it's rise over run, yeah, but I'm going to have to modify it a little bit because it's a scatter plot. I could work out rise over run in some way based on all the X values and all the Y values. But I need to then modify it a little bit based on how tightly correlated those values are. So once I get my rise over my run, and I put it in quotation marks because it's not the exact same as what you would do in high school. It's not going to be that simple. But I get some kind of mathematical description of some spread of the Y's, some mathematical description of some spread of the X's, and then I modify it by how tightly correlated they are and multiply it by the correlation coefficient. Okay? Does anyone want to take a guess? It's a scatter plot. What number might you use to represent the concept of rise? Okay, the difference in Y values. What might be a good guess for a number you could use? I want something to do with Y values, something that indicates how spread they are vertically, right? Any ideas what you might use? Keyword there is spread. Standard deviation, yeah. I'd use the standard deviation for the Y's to indicate my rise, and my standard deviation of the X's to indicate my run. So I'd look at a scatter plot like this, and the standard deviation of the Y's gives me some intuitive idea of how spread they are vertically, and some intuitive idea of how they spread horizontally. That would give me a rise over a run if I use the standard deviations. Then I modify that with the correlation coefficient by how tightly correlated they are. So here I have the formula. Sigma y over sigma x, rise over run. And this whole thing here is just R, the formula for the correlation coefficient. Again, I've used the form where it's in terms of z-scores, because that's going to be easy to work with. Generally, I think this formula is just better for every single purpose. There it is. Sigma y over sigma x, that's going to cancel out. There's a factor of sigma y in the numerator and the denominator that cancels out. And I'm left with sigma x times sigma x on the bottom. That's going to be sigma x squared. It's going to be the variance of the x's. And if I substitute in the formula for the variance, okay, squared deviations over n minus 1 for the x's, that's going to cancel out with a factor of n minus 1 from the correlation coefficient. And what I'm left with is this formula here, and this is the exact one that they said that you get for the estimate of B in the lecture slide, okay? SXY over SXX. That's where it comes from, okay? Again, if maths isn't your strong suit, don't stress. I just put it there for anyone who does, I mean, this is supposed to be university education. If you have done advanced maths before, at least now you know where that number comes from. You're not just plugging numbers in blindly. It is that same basic idea. I always try and draw it back to something that you understand intuitively. The slope estimate is still some rough idea of rise over run, okay? That's where it came from. Sigma y over sigma x, rise over run, then I modified that. I had to qualify that, okay? By saying, yeah, I can get a standard deviation of the y's and a standard deviation of the x's, but how tightly correlated are they, okay? I can get standard deviation for y's and x's for a blob that has a 0 correlation, okay? I should not be then getting a slope estimate out of that. There is no correlation. So I modify it with r, and that's what you get. So there it is, SXY over SXX. It's kind of like rise over run. So those are the two you need to remember. Basically, if someone gives you some sums of squares, you work out B hat first, your slope estimate, then you can work out A hat based on that and the means of the others. And this is what they do for us. They give us the numbers. They give us the mean of the metacarpal bone lengths and the mean of the statures. 45.44 millimeters roughly and 171.7 centimeters approximately, okay? And then they work out the sums of squares for us for the x's, the y's, and between the x's and the y's. Given that information, it's just up to you to then remember SXY over SXX. It gives you a slope estimate of about 1.7. Now that you've got your slope estimate, you can plug that into the formula. Y hat minus, sorry, Y bar minus B hat times X bar. Okay, plug in all those numbers and it spits out the y-intercept, the point where the line crosses the y-axis. It's as simple as that. Obviously, the maths is very complicated, right? All those formulas, there's a lot going on. But it boils down to remembering SXY over SXX and then remembering how to get A hat from the equation of the line. Okay. So to recap, we found that the line of best fit would be given by these particular numbers for a slope and an intercept based on the sample data, okay? Here's my sample data. Based on this particular collection of numbers, I can work out roughly what the slope should be and what the y-intercept should be for the line that best fits that data. So there you go. We've got basically a mathematical model. We've got a mathematical model that describes the relationship between metacarpal length and stature, if there is a real cause and effect relationship between them. We expect it for biological reasons, okay? As you saw from those examples, it's not always the case that correlation implies causation. But we expect it from simple arguments of anatomy, that it should be roughly proportional, okay? Your skeletal structure, again, there's going to be variation, but it should be roughly proportional overall. Obviously, a child would have a very small metacarpal, and that would be very short, okay? Someone like me would have a much larger one and a much taller height. You expect that relationship. We've quantified it now. We've quantified that linear relationship between those two variables, okay, with the equation of a line. Now, a couple of things we have to be careful of. The intercept, that's the value of y corresponding to when x is 0, may not always make sense, okay? It will tell you that when x is 0, you get this specific number, but that may not make sense physically. And we'll see that in a second when we do the example with the sample data. And the slope, this is important. This is a very, I like to call it an examinable question. Very common kind of question to be given is to be asked to interpret the slope in the context of the question. That's very specific. Remember in the pracs, I always say make sure you draw back to some kind of conclusion in the context of the question. For us, we're talking about bone and stature, metacarpus versus height. We got a number, 1.7. 1.7 was our slope for the line that best fit the data. Does anyone know what that means? How would you interpret that in the context in terms of metacarpal lengths and stature? It's okay if you don't. It's quite a... We'll get to that. The estimated slope was 1.7. How do I interpret that? Each increase of 1 millimeter in metacarpal length corresponds to an estimated increase of 1.7 centimeters in height. That's what it means. The slope is 1.7. It's rise over run, right? It's your y variable, height, over your x variable, okay? Height or stature over metacarpus length, okay? It is equal to 1.7. So for every unit that I increase in the x direction, I'm saying that I will increase 1.7 units in the y direction, okay? And now you have to be specific, very specific to the context of the question, starting with the units. Don't mix the units up. It's different units. They're both measurements of length, but the metacarpal in the data was measured in millimeters and height was measured in centimeters, so don't screw that up. And also, be specific to the question in terms of what are you talking about? Metacarpal and height. Here they've referred to just being taller, okay? So if you're asked this question in the exam, make sure you tick all those boxes. Were your units correct, okay, when you interpreted the slope? For an increase of how much, that corresponds to an increase of how much, specifically. Kilograms, centimeters, seconds, whatever. Has to be correct for both of them. They may not be the same. They may not be the same units, just like they are here, millimeters and centimeters. And you have to make sure that you mention the actual names of the variables, not just x and y. That says nothing about people's height and the length of this bone in their hand, right? Be specific to the context of the question. So that's what it means. Let's now use the actual equation. This is the equation that we got. This is the equation of the line, based on all of that information that we plugged in before. We got b hat 1.7, we got a hat 94.45, okay? Now this is a mathematical model. It's a very simple one. It means that I can make predictions based on these numbers. I can ask the question, for instance here, what would someone's height be, roughly, if their metacarpal length was... They haven't even done it on this slide. Never mind, it's on the next slide. What would their height be if the length of their metacarpal was 44 millimeters, okay? You plug it into the equation. Your stature is going to be 94.45 plus 1.7 times the length of the metacarpal. And we would estimate someone with that size bone in their hand to be about 170 centimeters tall, okay? What about 55 millimeters? So you plug in 55 millimeters into the formula and you get an estimate for 187 centimeters tall. It's as simple as that. Once you get over that hump, all that mathematics, all that stuff that really you don't need to worry about, it's as simple as plugging in a number to this plus that times that, okay? And even then, sometimes R Commander will do it for you. Obviously not in the final exam, but you know, you may be given output. You just have to read the number off, plug it in, okay? So there you go, that's what it's for. Couple of things. If I plug in a metacarpal length of 0 millimeters, I would get a height estimate of 94.45 centimeters tall, which does not make sense, okay? No one has a metacarpus that is 0 millimeters in length. It has to be some length, okay, from the moment you're born to the moment you die. It's got some minimum length. So that's the failing of the model, okay? All linear models will break down at some point. There is some range beyond which it doesn't make sense to talk about them anymore. Obviously, you can't still be a person. You can't be a person with this height if you don't have, you know, a metacarpal length of some finite amount, something bigger than 0. So the y-intercept doesn't necessarily always make sense. It may sometimes, but more often than not, it won't. Okay, so be careful of that. The y-intercept doesn't always make sense. The other thing we'll say is that the last example we had there, for 55 millimeters, that wasn't actually inside the range of the original data. The original data covered, let's have a look at the range, here we go. From 39 was the smallest to 51 was the largest. So 55 is outside the range of the original data. Now you've got to be careful. I can make a prediction. I've got my model now for my line, okay? Y equals A plus BX. I can plug in 55 into the formula as we did, and you get 187 centimeters for the height. Whether or not you should do that is risky because I don't have any sample data that covers that range. I should be careful about then applying the formula to things that aren't covered in that range. 55 millimeters is outside that range. As I said, all linear models break down at some point. Okay, we've proven that there is a linear relationship for numbers between 39 and 51. What happens outside of that, we don't know. When does it start to break down? Obviously, there's a minimum, right? What's a newborn's metacarpal length? There'd be a smallest value that it could possibly be. Beyond that, it would break down. Okay, it'd probably break down before then. The linear relationship would maybe start tailing off into something that looks exponential rather than linear. So we don't know where it breaks down, so you have to be careful about applying it to things outside of that range, okay? It may be in the breakdown spot. That's called extrapolating, okay? Extrapolating to numbers outside the range of the original data. So you just have to be careful. Sometimes it's justified, sometimes it's not. You just have to play it by ear, okay? Any questions so far? So here's graphically what we just did. We've got our scatter plot. The red line is our line of best fit. It crosses the y-axis. It's a bit annoying because you can't see it here. They didn't set the origin to be 0, 0. The 0, 0 origin maybe down here somewhere. 0, 0. This line would cross the y-axis at, I forget where we said it was like 90 something. So if we had the origin at 0, and there's my y-axis, the value of A was about 95 something, I think, roughly. Okay, so that was the y-intercept. That's all the y-intercept is. At what point does the line cross the y-axis? You'll notice that because most of our data was much further away from 0, 0, they didn't bother drawing the scatter plot all the way down to the origin because it would just take up a lot of empty space. It's not worth it. So if you did continue it down to where the real cross is, it'll be at 95 there. So that's your y-intercept. The slope is 1.7. So if you dial in at any point on this line and worked out the rise over the run, say take a point here and a second point there, what would be the rise over the run? It means that if I were to increase 1 millimeter in metacarpal length, I'd expect a 1.7 centimeter increase in stature. Okay, that's all it is. That's the gradient, that's the slope of the line. These purple lines here represent the predictions we just made. One of them was inside the range of the data, the other one was outside. We predicted, based on our linear model, that if you find an incomplete skeleton where the length of the metacarpal bone was 44 millimeters, you estimate that person's height to be about 169 centimeters. Okay? That's the power of the model. You only had 9 points of data in your original sample. That doesn't matter. You get the linear model. You can do it on anything inside of that range of the data and say, given this bone, what was that height, et cetera, et cetera. The next one was outside of that range. It's like 187, I think, for 55 millimeters. Okay? So maybe that's reasonable, maybe it's not. As I said, all linear models break down at some point. If you zoom out, at some point it may start sort of looking like this and tail off. And similarly at the top range, it might start tailing off, okay? Humans obviously don't have an infinite capacity for height or for the length of their hands, so this model is not going to work forever. Where it stops, we don't know. We do know it applies to the numbers within our range of our sample data. Outside of that, we're not so sure. Okay, so that's it. Y equals A plus BX. And just to be explicit, what was that for us? I don't even remember. What it was 94.45? 94.45 plus 1.7 times X. Okay? That was all of what that work was for, to get that single equation. Okay? It's a linear model that best describes the relationship between those two quantitative variables. All happy? Yep. So the last thing is, again, the assumptions that we made when we did simple linear regression. The real relationship should be linear, obviously. That's one big assumption that we made. We weren't sure of that. Working out the correlation coefficient helped us probably guess that that was going to be the case. It seemed very likely based on the correlation being so high for a linear correlation. The observations, again, should be independent of each other.
the variation around the line should be normally distributed and should not depend on x. That's one thing that's probably worth pointing out. I get my equation of my line. I'm not expecting the line to be perfect, right? Every time I estimate some values or measure some real values from the population, I get, say, 10 people together who all have a metacarpal length of 40 millimeters, okay? If I get those 10 people together, I might expect their heights to be, you know, distributed in some way like this. Something that looks like a normal distribution. I shouldn't have too many people too far above the predicted value or too far below it. It should be centered on the predicted value in a way that looks pretty like normally distributed in terms of its density. That should be the case, whoops, for every single point on the line. If I cared to make measurements for people with the same length metacarpus, what is their height? I expect them to be distributed around the line roughly in this way, in a way that is normally distributed. I also expect that variance to not change. If I went up here to say 53, well, let's go a bit further down. Let's say I still got something that is normally distributed. So I take maybe 100 people. I get a lot of numbers around the center. I get a few far away from that. It's still normally distributed, but now the variance is much bigger. It looks like a much wider normal distribution than the one I had down the bottom. Okay? This is something we don't want to see. If we're expecting a linear relationship, I should not get the scatter plot sort of fanning out as I move. Okay? As you increase or change the value of the predictor variable, I should not expect a change in variance around that line. I'm expecting it to be pretty, you know, tightly clustered within sort of a corridor. Either side of the line, the variance should not change. There's going to be variation around the line, but it should not change depending on where you are on the x-axis, okay? And that should be it. Any questions? Pretty tough lecture, I'll be honest, but that's what the practicals are for. Everything that you saw that scared you, you should hopefully settle once you do the prac for this kind of material, because you see that it's not that difficult. You'll be using RCommander, reading output from RCommander, plugging in some numbers to a very simple equation. Okay, it should be quite simple once we get down to brass tacks. All right, thanks, guys.